What if the force holding you to Earth is not actually a force at all? Right now, you feel your body pressed against the chair, the floor beneath your feet, the weight of your own bones. Everything about that sensation seems to say the same thing. Earth is pulling you downward. For centuries, that was essentially how physics described gravity. But Einstein discovered something far stranger. If you were falling freely toward Earth with nothing stopping you, you would not feel gravity at all. The moment you hit the ground and stop falling, that is when you feel a force. And hidden inside that simple reversal is one of the most profound ideas in modern physics. Perhaps gravity is not something pulling objects through space. Perhaps gravity is what happens when space and time themselves refuse to stay flat. This sounds almost impossible because Newton's picture of gravity works so well. Drop an apple and it falls. Throw a ball and it follows an arc. The moon circles Earth. Earth circles the sun. And Newton's law of universal gravitation can describe all of them with extraordinary accuracy. Newton imagined gravity as an attraction between masses. Every object in the universe pulls on every other object. The strength of that attraction becomes weaker with distance and stronger with mass. With one mathematical law, Newton connected falling objects on Earth to the motion of the heavens. It was one of the greatest achievements in science. But Newton himself understood that something about gravity was mysterious. The sun is about 150 million kilometers from Earth. Yet in Newtonian physics, its gravitational influence seems to act across that enormous distance. There is no visible rope connecting Earth to the sun, no mechanical gears, no obvious medium carrying the pull. Gravity simply acts. For more than 2 centuries, the equations worked so beautifully that physicists could calculate planetary orbits, predict eclipses, and even infer the existence of unseen worlds. But eventually, nature exposed small cracks in Newton's picture. One of the most famous involved Mercury. Mercury's orbit is not a perfect ellipse permanently fixed in space. The closest point of its orbit to the sun slowly shifts. Most of this motion can be explained using the gravitational influence of the other planets. But after every known Newtonian effect was accounted for, a small discrepancy remained. It was tiny. But physics sometimes changes because of tiny discrepancies. By the beginning of the 20th century, another revolution had already begun. Einstein's special theory of relativity had declared that the speed of light is fundamental, and that space and time cannot be treated as completely separate things. And that created a serious problem for Newtonian gravity. If the sun somehow disappeared, Newton's equations seemed to imply that Earth's gravitational response would occur immediately. But special relativity says information cannot propagate faster than light. Something had to change. Einstein's path toward the answer began with an idea so simple that he later regarded it as one of the happiest thoughts of his life. Imagine a person falling from a roof. Ignore air resistance. Ignore the danger. Imagine only the physics. As the person falls, everything they release falls beside them. A coin released from their hand appears to float. Their keys appear to float. For a brief moment, the person experiences weightlessness. Yet according to the ordinary description, gravity is acting strongly on them. Why can't they feel it? Now reverse the situation. Imagine yourself inside a rocket far from every star and planet. The rocket's engine turns on accelerating upward. The floor pushes against your feet. If the acceleration is approximately equal to Earth's surface gravity, you could stand inside the rocket and feel something remarkably similar to weight. Drop a ball and it appears to fall toward the floor. But there is no planet beneath you. There may be almost no gravitational field around you at all. The ball is not being pulled downward. Instead, the accelerating floor rises toward the ball. Einstein recognized something extraordinary. Locally, being in a gravitational field and being in an accelerating reference frame can look remarkably similar. This became the equivalence principle, the conceptual heart of general relativity, and it changes the meaning of gravity. Leonard Susskind often approaches relativity by forcing us to abandon comfortable pictures and follow the equations and thought experiments wherever they lead. In the framework of general relativity, a freely falling observer follows the most natural path available through spacetime. That observer is not, in the relativistic sense, being forced away from natural motion. The person standing safely on Earth's surface is. That sounds backwards, so imagine dropping 2 people from a very tall tower inside perfectly sealed capsules. As they fall, each person feels weightless. Their bodies do not feel some mysterious downward tug passing through every cell. They are following free fall trajectories determined by space-time geometry. Now consider you standing on the ground. You are not falling. Why? Because the ground is preventing you from following the free fall path you would otherwise take. The atoms in Earth's surface resist being compressed. Electromagnetic interactions between atoms keep the ground solid. Those interactions push upward on your feet. That upward push travels through your body. That is what you experience as weight. In other words, the sensation you normally call gravity is largely the sensation of being prevented from falling. An accelerometer makes this distinction beautifully. Place an accelerometer on the ground and it registers an upward proper acceleration. Let it fall freely and ideally it reads 0. The falling accelerometer is moving toward Earth faster and faster, yet locally it regards itself as unaccelerated. The stationary accelerometer looks motionless, yet it detects acceleration. The deeper you follow this logic, the stranger reality becomes. Einstein realized that gravity could not merely be added to special relativity as another ordinary force. Instead, mass and energy would have to change the geometry of space-time itself. To understand what that means, forget gravity for a moment and imagine two people walking on what they think is a flat surface. If they begin side by side and walk in perfectly parallel directions, they should remain the same distance apart. But place them on Earth. Start both at the equator and have them walk north along different lines of longitude. At first, their paths appear parallel, yet eventually they meet at the North Pole. Neither person turned toward the other. The geometry of the surface caused paths that began parallel to converge.
General relativity takes this idea into four-dimensional space-time.
Objects moving freely follow paths called geodesics. In flat space-time, these paths behave one way. In curved space-time, they can converge, diverge, and bend relative to one another. A planet orbiting a star is not necessarily being dragged around by an invisible gravitational cord. In Einstein's description, the planet is following a geodesic through curved space-time. The sun changes the geometry around itself. Earth moves through that geometry. The result is what we interpret as an orbit. The common analogy is a heavy ball placed on a stretched rubber sheet. Smaller balls roll toward it because the sheet is curved. The picture is useful, but dangerously incomplete. The rubber sheet bends downward because Earth's gravity is pulling it downward, meaning the analogy secretly uses gravity to explain gravity. Real space-time does not need to curve into some visible extra dimension. Its curvature is intrinsic. The geometry itself changes, and time is just as important as space. In fact, near ordinary objects like Earth and the Sun, the curvature involving time plays an essential role in producing what we experience as gravity. Clocks run at different rates depending on gravitational conditions. A clock closer to Earth runs slightly slower than one farther away. This is not an optical illusion. It is measurable. Modern satellite navigation systems must account for relativistic clock effects. Without relativity, positioning errors would accumulate rapidly. So when general relativity says space-time is curved, this is not philosophical language. It has practical consequences in technology operating above our heads every day. But another mystery immediately appears. If gravity is not a force, why do objects fall faster and faster? Because velocity depends on how space-time is being described. A freely falling object follows a geodesic, but relative to an observer standing on Earth's surface, its downward speed increases. The standing observer is maintaining a non-free fall trajectory. Different observers divide space-time into space and time differently. An acceleration can appear in their coordinate descriptions even when the falling object experiences no proper force. This distinction becomes dramatic near a black hole. Black holes are where Susskind's work has repeatedly tested our deepest assumptions about gravity. Imagine falling toward a sufficiently large black hole. From far away, the object sounds terrifying, an immense gravitational monster from which not even light can escape beyond the event horizon. Yet if the black hole is large enough and tidal forces at the horizon are mild, a freely falling observer could cross the event horizon without encountering a solid surface or a sudden local gravitational wall. There is no alarm built into space-time announcing, "You have crossed the horizon." Locally, the falling observer continues along a free fall trajectory, but to a distant observer, the story is described very differently. This tension between observers became central to the black hole information problem and to ideas Leonard Susskind helped develop, including black hole complementarity. It also reveals why the simple phrase gravity is a force becomes inadequate in extreme environments. Near a black hole, gravity is not just stronger Newtonian attraction. The causal structure of space-time itself is radically altered. Light cones tilt. Paths that once could lead outward eventually point only deeper inward. The geometry determines what futures are physically available. And yet there is a complication that prevents us from casually saying that gravity does not exist as a force under any circumstances. General relativity eliminates gravity as an ordinary force locally for a freely falling observer, but gravitational effects cannot always be transformed away over an extended region. Imagine two astronauts falling toward Earth from slightly different positions. Both feel weightless, but their trajectories may slowly approach one another because both are falling toward Earth's center. Place another pair at different distances from Earth, and they may accelerate differently. These relative effects are called tidal effects. They reveal space-time curvature. You can choose coordinates that remove gravity at one point or along one freely falling path, but you cannot generally remove space-time curvature everywhere. This is crucial. The statement gravity is not a force is a useful description of Einstein's geometric theory, but it should not be misunderstood as saying gravitational phenomena are unreal. Tides are real, orbits are real, black holes are real astrophysical objects. Gravitational waves are real disturbances in space-time geometry and have been directly detected. What changed was our understanding of what causes those phenomena. Newton said masses exert gravitational forces. Einstein said matter and energy shape space-time geometry, and freely moving matter follows that geometry. John Wheeler later summarized the spirit of general relativity with a famous formulation. Matter tells space-time how to curve, and curved space-time tells matter how to move. But even that elegant picture is not the final story, because Einstein's theory and quantum mechanics do not comfortably fit together at the deepest level. And this is where Leonard Suskind's field becomes unavoidable. General relativity treats space-time as a smooth geometric structure. Quantum mechanics tells us that nature at microscopic scales is governed by quantum states, uncertainty, superposition, and fluctuations. Try to apply both theories in extreme situations, inside black holes or near the earliest moments of the universe, and serious conceptual problems appear. Physics, therefore, needs a quantum theory of gravity. String theory is one major attempt. In perturbative string theory, the fundamental objects are not dimensionless points, but tiny one-dimensional strings. Different vibrational states appear as different particles. Remarkably, one of those states has the properties expected of a graviton, the hypothetical quantum particle associated with gravitational interactions in a quantum description. This means something fascinating. At one level, general relativity tells us gravity is geometry rather than an ordinary force. At another level, quantum theories can describe gravitational interactions using particles such as gravitons. These viewpoints are not necessarily contradictory. Physics often allows the same phenomenon to be described in different languages, each useful in different regimes. Electromagnetism can be described through fields and through quantum particles called photons. Gravity may similarly possess both geometric and quantum descriptions. But gravity has a special relationship with spacetime because the gravitational field is spacetime geometry in general relativity. Quantizing gravity, therefore, means, in some sense, quantizing the geometry of the stage itself. That is, unlike ordinary forces. In quantum electrodynamics, photons move through spacetime. In quantum gravity, the structure defining what through spacetime even means may itself fluctuate. And this opens the door to one of Suskind's most influential areas of thought, holography. The holographic principle arose partly from the strange thermodynamics of black holes. Black holes possess entropy proportional not to their volume, but to the area of their event horizon. That fact suggested something deeply unexpected about gravity and information. Perhaps the maximum amount of information associated with a region does not scale with the amount of space inside it. Perhaps it scales with the boundary. Susskind became one of the strongest advocates of this idea. Later, Juan Maldacena's AD-SCFT correspondence provided a precise example in which a gravitational theory in a higher dimensional spacetime can be equivalent to a quantum theory without gravity living on a lower dimensional boundary. The implications are enormous. Gravity in one description may emerge from a completely different quantum description. Even spacetime itself may be emergent. This remains an active area of theoretical physics. We do not yet possess a complete experimentally verified theory explaining exactly how the spacetime of our universe emerges from microscopic quantum ingredients. But the possibility changes the original question again. If gravity is geometry, and geometry itself might emerge from quantum information, then gravity may be telling us something deeper than how objects attract one another. It may be revealing how spaces assemble. Research connecting quantum entanglement with spacetime geometry has strengthened this suspicion in certain theoretical settings. Entangled quantum systems possess correlations that cannot be understood classically. In holographic models, patterns of entanglement are closely related to geometric properties of the corresponding spacetime. Reduce certain kinds of entanglement in theoretical constructions, and the associated geometry can behave as though regions of space are pulling apart. Again, this does not prove that ordinary space around you is simply made of entanglement, but it suggests that geometry and quantum information may be more deeply connected than physicists once imagined. Think about how far gravity has traveled conceptually. It began as the mysterious tendency of objects to fall. Newton transformed it into a universal force extending across the heavens. Einstein transformed that force into geometry. Black holes connected geometry to thermodynamics. Quantum theory connected black holes to information. Holography then suggested that gravity and spacetime might themselves emerge from a deeper description. And still, you can discover Einstein's original insight simply by stepping off a ledge. For one terrifying moment before air resistance and impact matter, you fall. The ground disappears beneath you. Your stomach seems to rise. And if you were enclosed in a perfectly isolated falling laboratory, small enough that tidal effects were negligible, many local experiments could not tell you that you were falling in Earth's gravitational field at all. Now return safely to the ground. Your feet stop. The Earth pushes upward. You feel heavy again. The force you feel is not some invisible hand dragging you downward. It is the ground refusing to let you follow the path space-time was offering you. That reversal is more than a clever physics fact. It exposes a recurring pattern in science. Reality often appears obvious only because we have spent our entire lives trapped inside one particular perspective. The ground looks stationary. The falling object looks accelerated. Space looks like an empty container. Time looks universal. Gravity looks like a force. Then physics changes the observer, changes the scale, or changes the question, and the familiar picture falls apart. There is still much we do not understand. General relativity has passed extraordinary experimental tests, from the motion of planets to gravitational lensing, gravitational time dilation, binary systems, black holes, and gravitational waves. But it is still a classical theory. At sufficiently extreme quantum scales, we expect it to be incomplete. String theory, holography, loop approaches, and other programs attempt to move beyond that boundary, but no complete theory of quantum gravity has yet been experimentally confirmed. Somewhere between Einstein's curved spacetime and the quantum world may lie a deeper explanation of gravity. Perhaps gravitons will emerge naturally from the correct microscopic theory. Perhaps spacetime itself will turn out to be constructed from quantum relationships. Perhaps concepts like distance and geometry will survive only as approximations, meaningful at large scales but absent in the fundamental description. And if that happens, the statement that gravity is not a force may turn out to be only the beginning, because Einstein taught us that what feels like a force can actually be geometry. The next revolution may teach us that what looks like geometry is actually something else. So the next time you stand quietly on Earth and feel your own weight, consider what is really happening. Far beneath your feet, matter holds the planet together. The planet changes the geometry around it. Your natural free-fall path leads inward. The ground interrupts that path. Electromagnetic forces between atoms push against you. Your body interprets that resistance as weight. And above you, the moon follows its geodesic around Earth, while Earth follows its own path around the sun, all moving through a space-time whose geometry is constantly shaped by the matter and energy within it. Nothing needs an invisible gravitational rope. Nothing needs a cosmic hand pulling from a distance. The geometry is enough, at least according to Einstein. But if Susskind and other quantum gravity theorists are pointing towards something deeper, If spacetime and gravity themselves emerge from quantum information, then even geometry may not be the bottom layer of reality. And somewhere beneath the falling apple, beneath the curved spacetime, beneath the black hole horizon and the equations describing quantum strings, there may be a final question physics has not yet learned how to ask. If gravity is not fundamentally a force and space-time may not be fundamental either, then what exactly is doing the falling?